compression is because this force have to counter the FAC over here. Okay, or not, we're going to have issue. Right. So with that, this is how we this is I think those of you in mechanical engineering, you don't usually draw multi-body free body diagram. Okay, so this is what we classify as multi-body. So this is what we have done in this example also. We draw a what? Multi-body free body diagram. Okay, so this might be the first time you're seeing it. Get used to it. We'll be applying this a lot of times later in the course also. Okay, so this is a so once you got the free body diagram set up, okay, so what we are going to do, we are going to use what we have drawn in terms of free body diagram. So the forces that we are going to focus on, I'm going to highlight them. Okay, so these are the force vector that we're going to focus on. Okay, these are all the force vector. So this problem is we have to, just to refresh your memory, we have to determine the allowable mass that the structure can carry at point C. Okay, so I'm going to put an M down here. The mass, we don't know what is the mass that we can carry. Okay, so as like before, we are going to determine. Okay, we're going to determine FAB. Okay, we're going to determine FAB. But before we do that, okay, before we determine FAB, so if I have to draw the transformation again, okay, if I have to draw the transformation again, so this is our X and Y, and this is our rotation Z. Let's form the equation for FAB first. Okay, I think that's more important for now. Then later on, we are going to look at how to check the possibility of the structure buckling along AB, or along the XY plane and along the YZ plane. That will affect your equivalent length. Okay. So for now, we are going to determine our FAB. So we are going to apply static analysis. So we're going to have we're going to focus at point A. Okay, static analysis at point A. So positive is coming out. Summation of forces in the y direction is equal to 0. So we have FABY, which is going up, and minus FADY, and then minus FAC. The whole thing is equal to what? Is equal to 0. Okay. So we're going to do this in terms of FAB. Okay. So we are aware that this angle over here, right, given to us, this angle is 60 degrees. And given to us, this angle is 45 degrees. Okay. So this, we can rewrite them as FAB sine 60 minus by FAD sine 45 minus by FAC is equal to 0. Okay. So if we do sine 60, is 0.866 FAB minus by 0.707 FAD minus by FAC. The whole thing will be equal to 0. Okay. Then the next thing that we carry out a summation of forces in the x direction. Okay. So what we have is, so going towards the right is positive, going towards the left is negative. So we have ABX, okay, or FABX, because it's going towards the right, and then minus FADX. Okay, so ADX is going towards the left, minus FADX. The whole thing is equal to 0. Okay. So from here, we can write down FAB. ABX will be cos 60 minus by FAD cos 45. The whole thing will be equal to 0. So cos 60 is equal to 0.5 minus by 0.707 FAD. So I'm going to call this my equation 1. My equation 2. Why I use FAB? Okay, well, I want to form it based on FAB, not ABX, ABY, or ADX, ADY. So I will reduce my number of variables. Okay, because we can only form what? We can only form 2 equations. Okay, if you have too many variables, we might in trouble. So from here, we can on equation 2, or I won't call this equation 2. We can also formulate that FAD is equal to 0.5 FAB divided by 0.707. So this is equal to 0.5. So it's 0.707 FAB. Okay. This is our equation 2. So from here, the critical thing is equation 1, FAC is actually what we want to determine, because from FAC, we can determine the load. Okay. So from here, we can substitute equation 2 into equation number 1, right? So what we have is 0.66 or 866 FAB minus by 0.707 FAD, which is 0.707 FAB. Okay. And then minus FAC. The whole thing will be equal to 0. Okay. So FAB, so 0.707 multiplied by 0.707, 0.866 minus by, so you get 0.366 FAB is equal to FAC. Okay. So you can write out that FAB is equal to FAC divided by 0.366. So 1 divided by 0.366 is equal to 2.732 FAC. Okay. Right. So now the next thing we have found is relationship over here, and this is our relationship number 3. Okay. So the next thing that we're going to find out, we are going to determine, okay, which plane the structure will buckle. Okay, we don't know. So let me get the picture again. Let me, in fact, I will do on the next page, which plane will buckle. So I'm going to get this image again. So I'm going to still call this our X, Y, and this is our rotation about Z. Okay. So if we were to look on the XY plane, which is what we are looking now from the XY plane, right, at this point of view. So if I'm going to draw the member over here, okay, so this is our beam. Oh. Okay, so this is our beam. Okay, so this is our point B. And this is our point A. And it can be observed, okay? It can be observed that over here on this end, point B, right, it is pinned, right? It's pinned because moment at point B is equal to 0. Okay, so the structure can rotate. At point A, we also realize that if we look at the forces that are applied, okay, so we are aware that there is a forces in the y direction, and there's also a forces in the x direction. Okay, right? But there's no resistance in what? Moment at point A is equal to what? 0. Okay. So when this is the case, the top is also what? Pin. Okay. And the top is also what we call P. So we realize that from the XY plane, both ends are pinned. So LE is equal to what? Okay, so based on this table, both ends are pinned, right? So both end pins, we know that LE, right, from here, LE is equal to what? L. Okay, so this is for the XY plane. Okay, now we are going to do from the YZ plane. So YZ plane, we are going to put our eyes in this direction. Okay, we're going to view the structure. So when you view the structure, this is now our member AB. Okay, so member AB. Okay, this is a point A. This is a point B. And then based on right hand rule, this is now your Y, and this is your Z, and this is rotation about X. Okay. So from here, if the structure is going to be buckle, the structure will buckle, right, along this plane. So if I were to draw the pinpoint, okay, so this is a beam down here, a separate component, right, and the pin is across it. So there's a resistance about what? Moment. Okay. So over here, moment is not equal to what? 0. So this is fixed. Okay. So this end is for this case, this end is going to be what we call fixed. At point A, right? We know, I'm going to draw this in red. We know that this vertical is how our FAC will behave, right? And then over here is just a dot over here, right? And this is the dot represents your your fx,